Now we shall discuss about image segmentation based on graph cut techniques. So the main objective of this graph cut is we are going to partition an image into regions by considering the pixels in the image. So you can see here I have an image with different colors, so that each and every color is representing here a pixel here, right? So these pixels are converted into a nodes in the graph, because we know that a graph is a combination of edges as well as vertices. The vertices are familiarly called as nodes in the graph. So each and every pixel are converted here into the nodes in the graph. Thereafter, we just do the partitioning the graph into a group of nodes. So one group is having similar features with respect to the other group. So as you know that a graph is denoted with G here. So a G is mathematical structure that is represented as a set of V and E, where V are nothing but it is the number of nodes, V number of nodes, and set E nothing but E number of edges that are connecting those V number of nodes here. So pixels of an image as nodes of a graph. So you can see here these pixels of an image are nothing but they are the nodes of a graph, and each and every node is getting connected through an edge here. Ultimately need to find an optimum partitioning of the graph, right? So let us see how it is going to happen. Now what is this graph cut? A graph cut is nothing but it is the weighted graph is split into disjoint sets according to similarity. Before it, we should understand what is this weighted graph. In the figure above and in this figure below, I don't have any values given to this graph. But here you can able to find some values are being given to the edges that are connecting each and every node. So a weighted graph is the one in which a weight is associated with each edge here. So that means each and every edge is having certain weight. So here a weighted graph is split into disjoint sets according to some similarity. The similarity may be texture, color, or intensity, or whatever it is. Right. So a graph cut is a grouping technique in which the degree of dissimilarity between these two groups is computed as the total weight of the edges removed. Okay. So let me assume that I am having group A and group B. So this group A and group B is wrapped with some volume, right? In this volume, I am having group A pixels as well as the group B pixels. So W of a P comma Q is nothing but it is the weight, right? It is the weight associated with the corresponding edge. Like W of P comma Q is this edge. That means it is this edge is connecting the point pixel P with the point pixel Q. So here P belongs to A group and Q is belonging to B group here. So W of P comma Q is nothing but it is the weight associated with the edge that connects P and Q pixels in the given graph. So as you can feel that a graph whose edges are associated with weights are nothing but here the weighted graph. Now what I am doing here is I am just partitioning the nodes, because each and every vertex of a graph is nothing but it is a node. So partitioning the nodes of the graph into two disjoint subsets here, right? So because as I have said you, a graph is having V number of vertices and E number of edges. So let me let me name each and every node as V1, V2, V3, V4 up to V number of nodes here. So that means K number of nodes. Okay. So V suffix K. That means in this graph is having K number of nodes. Let us assume. So partitioning the nodes of the graph into two disjoint subsets like V1, V2, V3 up to some V's, and here also like V7, V8, V9, V10 up to some number of V's will be coming under B group. Now the similarity among the nodes, because this is having more similarity, right? So this forms a subset, okay, and the similarity, because these all are in ash color, this forms one group, right? So the similarity among the nodes within a subset is high here, as you can see, and the other subset is also high here. A group is having the similarity is more, and in the B group the similarity is more. But if you connect a point from here, and if you connect a point, if you pick a point from here, there will be a dissimilarity. So this have to be avoided. So the nodes of the partitioned subsets corresponding to the region, this is one region in the segmented image, and this is also one region in the segmented image. So that means this number of nodes entire, that means this set V, which is having A group and B group inside it, is partitioned into two subsets A and B by cutting the graph. Can I write now A union B equal to V, as well as A intersection B equal to 5? That means none, no element here. So let me explain you the similarity concept by taking one example. The degree of similarity between the two pixels is the inverse of the difference in their intensities. So this is an image in which we can able to see a tiger eating something. So if I give this input image to the graph cut algorithm, what the graph cut algorithm, it will segment the object of the tiger with one label and the background with other label, right? So that means there is a pixel in this image that is located on the body of the tiger here. So this is my first pixel and this is the second pixel. So these two pixels are similar in nature, right? So if they are similar in nature, means they are having the capability to form a region. That means if the intensity that is present over here is around 190, and if it is like 175, that means these two pixels are very similar in nature or intensity. So they can able to form a group. Now if they are able to form a group, means definitely the pixel are joined here by using an edge. And if there is a edge present, means definitely weight also be associated with it. W of I comma j, because this is my ith pixel, this is my jth pixel, is nothing but it is the 1 by I of ni minus I of nj plus some c. These I of ni and I of nj are nothing but they are the intensities of the two vertices or two nodes or two pixels, and c is some constant. So that means it is the weight. So weight is inversely proportional to intensity here, right? So like that means here, if this entire tiger object is connected, the pixels that are present on this tiger object are connected with certain links. So there will be a link between every pair of pixels on the similar regions, right? Now I would like to explain the same concept, that is I just wanted to interpret the graph as a flow of network. That means through pipes. So here this is my source, this is my bore, and from here I will be collecting the water, and this water will be released into the bucket. So these are the some number of pipes in between this one and this one. So I would like to interpret the graph now as a flow of network which is happening through the pipes, and my main intention is I need to obtain the minimum graph cut. If I do my cutting in appropriate way, for example like this, if I cut means I need to cut here, 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 here. That means 8 number of cuts I am doing here. Or if I make a cut at this cross section, means 1, 2, 3, 4, 5, 6, 7, 8. 8 number of cuts also I need to perform here. So my aim is I need to perform a cut such that it should be a minimum. That is, let me explain now it clearly. I need to do a minimum graph cut. So because this first pipe is the one, right, which is linking from this node to this node. So I have to cut, I have to make a cut here, and from this node to this node, this is the main stream flow. So I need to cut the pipe here, and here also I need to cut, because if I cut the pipe here means it is of no use, right? So that means if I do the cutting operation at this area or at this area, I have to do 8 cuttings. But if I do it by applying my intelligence means it is a minimum cut. So here I will be applying, here I will be applying, here as well as here and here. So this formulation is nothing but it is a minimum cut. So minimum cut means to where we are doing the minimum cut to maximum flow. So from along this region only, wherever I am cutting from like through those pipes only, there will be a maximum flow of water, right? Direct linkage is there from this group to this group, from this part A to part B. So this is about minimum cut. That means where there is a maximum flow, that I need to cut here. So this theorem states that in a flow of network, the maximum amount of flow here passing from source to sink is equal to the minimum cut. So this minimum cut is given by this expression, that is cut of A comma B equal to W of U comma V. So U belongs to this region, that means it is some node, V belongs to some node in this group, right? So that means it is defined as the smallest total weight of edges, right? Because it is the smallest weight of the edges only, right? Because if I do the cutting in this manner means it ultimately leads me a heavy cost that should be avoided. So it is a smallest total weight of edges that if removed would disconnect the sink from source. So this is about maximum flow minimum cut theorem. So in this graph cut based technique, first thing is we need to understand about graph, like it consisting of vertices as well as the edges. And if I do the graph cut, that means I am doing the partitioning or dividing into 2 groups here. That is the cutting operation intention. And after that one, we have studied about the similarity between the pixels, and there is a theorem called minimum cut theorem. So minimum cut theorem is highly applicable such that the weight or the cost function will be reduced here. But sometimes what happens, even though the minimum cut approach offers a best solution, but it can give a result in grouping that favor cutting small sets of isolated nodes or vertices in a graph. So that means it is some isolated vertex, right? Or isolated object here and isolated object here. So if I do the cutting operation for this one and this one, does it make sense? No, right? Because if I do a cutting operation means there is a judgment that have done for cutting. That means a weight, a cost function is justified here. But if I do the cutting operation at this area or at this area, the cost function is not justified because we are spending much amount, right? So that have to be avoided. That means the minimum cut approach here offers an improper or inadequate segmentation, right? That means it is a meaningless segmentation. Now what I would like to do is, like, instead of looking at the total weight value of the edges here, so total weight, instead of looking at a total weight value of the edges, this is connecting the 2 groups. This is one group and this is one group. My idea is I would like to measure the disassociation between the nodes. So this association between the nodes means the nodes are connected with each other through an edge, right? So if the 2 nodes are not similar, that means there exists some disassociation that computes some cost as a fraction of total edge here. So that means that my idea is to measure the disassociation that computes my cost function as a fraction of total edge connections to all the nodes in the graph. So let me explain you it bit more clear. So disassociation between group A and group B and the maximization of the association within each group. This is my ultimate objective of the normalized cut. Previously we have seen graph cut. This is max flow minimum cut theorem for that graph cut, and there is a drawback in this max flow minimum cut theorem. So to overcome that one, we are going to study about normalized cut. So I do have here a group of nodes which are of a family of A, and these are group of nodes. This is of family B. So A, B, A, B. So association of A comma A, and this will be association of B comma B. That means all the nodes within group A are associated with each other, and all the nodes within group B are associated with each other, and the relation between A and B is a cut. So A and B are related with cut of A comma B, and similarly B to A is also related with cut of B comma A. Now let me explain you this concept here. So as I have said you, n cut. So n number of cuts I need to perform from A to B. So I just replace this cut of A comma B with n cut of A comma B. This is normalized cut equal to cut of A comma B by association of A comma B plus cut of A comma B with by association of B comma B. Now association of A comma A is nothing but all the edges here, plus cut of A comma B means this edge, right? So this one, that means it is tending to join with some other group vertex, right? And this node is also tending to join with some other group nodes here. These are nothing but these are the cuts. So here this association of A comma B equal to summation of U belongs to A and Z belongs to B, because A and B are the elements or the groups that are present in the superset of V. Means in the superset of V there may also exist some other number of vertices, right? May exist or may not exist, right? So A comma B equal to sigma U belongs to A, Z belongs to V. These are some nodes which are present in the superset of A and B. Okay, so they are tending to connect with V here. They are tending to connect or join with here Z. So Z is nothing but the number of nodes. What I have said U belongs to A and V belongs to B, right? I have taken one more number of nodes because this is UI, U1, U2, U3, U4. Let me call like this. This is V1, V2, V3. There may also exist Z, which are present in the superset V, such that Z1, Z2, Z3, some n number of Z's nodes are also may present. So that means can I write association of A comma B equal to sigma U belongs to A, Z belongs to B, weight of U comma Z. That means this weight is nothing but it is joining the node U which is belonging to A with the node Z that is present in V. So the equation is the sum of weights of all the edges from the nodes of the subgraph A to the nodes of the entire graph. And similarly association of B comma B equal to sigma V belongs to B, Z belongs to B. How we have analyzed the equation? In the similar manner you need to analyze the same equation here. So Z belongs to B and W of V comma Z. So this is nothing but it is the sum of weights of the edges from all the edges in B to the entire graph. Now finally I need to find out n cut of A comma B. So as you have seen, right, n cut of A comma B equal to, in the previous equation, cut of A comma B by association of A comma B plus cut of A comma B by association of B comma B. So I can write cut of A comma B as, so this is cut of A comma B. Let me write as association of A comma B minus association of A comma A. I have written. So just substitute these things, these relations in this equation. Finally, I am going to lead 2 minus n association of A comma B. So it implies that minimizing the n cut of A comma B happens once my maximizing, if I maximize the n association of A comma B. So these two simultaneously happens. These are the normalized cut results, where you can able to find how this normalized graph cut is performing the segmentation process. Thank you. Have a nice day.